Hey kids, today we're going to be talking about water and pH. It is your responsibility to go over the notes and make sure that you have all of the stuff on your note taker written down. If you need to pause this to slow down, by all means go ahead and do that. And at some point in time today, I will be pulling students off to the side and we're going to be doing some labs. So you're going to figure out what some of the things are in this video based off of what we do in class together. So let's kick things off. Your key question for today is, why is it important for your cells in your body to buffer against solutions that are really, really acidic or really, really basic? Your body is mainly water, and so hopefully at the end of this you see why water is so vital and why we want to keep it as such. And then we're going to talk about acids and bases towards the end of this lecture. So water is essentially the greatest liquid ever. It kind of looks like a Mickey Mouse. It's got two hydrogens that are positively charged and a negative oxygen. So that causes this kind of push and pull in between the water atoms. So we're going to be looking at polar molecules, hydrogen bonding. Why does ice float instead of sinking? Acids, bases, along with that pH scale. So because we have a positive and a negative here, water is polar, just like a magnet. It literally has positives and negatives like magnets do. Because of that, in some instances, people will take super strong magnets and hold them next to like slow dripping faucets, and you can even see the water bend a little bit, just like Aang in Avatar: The Last Airbender. So opposites attract here. We have positive poles and we have negative poles. And because water has that positive and negative, they end up kind of clicking together in this beautiful fashion that you can see down at the bottom. You've got the oxygens that are closer to the hydrogens, and the hydrogens are a little bit closer to the oxygens. Opposites attract in this case. So because of this, we end up seeing water when it gets cold and it's not able to move anymore, locking into this really, really rigid structure. Whereas when it's a liquid, all of the hydrogens and oxygens kind of slip and slide over each other. There's still a lot of movement there. So solid water is less dense than liquid water is, which is why ice will float. Water is also a solvent. I know it's kind of hard to see here. There we go. Water is a solvent, which means that it can dissolve other things. Solvent is going to be another word for like the larger liquid that is involved. Sometimes, let's say you're making Kool-Aid, water is the solvent, the Kool-Aid and the sugar are going to be the solutes. So in this instance, we have water, and water is polar. They are surrounded by other water molecules and atoms, and sometimes if you add in another solution, that other solvent can also be polar, and that's when we end up dissolving it. So a solute is the thing that gets dissolved in the solvent. I always think about solutes being smaller than solvents, which in general, if I dissolve salt into water, there's way more water than there is salt. So the word solvent is larger than solute. We end up saying much more solvent. So sodium chloride, otherwise known as table salt, is polar. The sodium is a positive charge and the chloride has a negative charge. So when we see these atoms lining up, the sodium will be surrounded by all the negative oxygens and the chloride will be surrounded by all the positive hydrogens. Opposites attract, but it needs to be polar in order for that rule to be true. So salt and water, the salt will dissolve in the water, but water and oil don't mix. They don't. You see all these little bubbles, and the oil is just kind of like rising up to the top. It's not mixing in. And even if you were to try to stir it, there would still be bubbles. Eventually, the oil would settle at the top and the water would fall at the bottom. So why don't they mix? Water is polar and oil is non-polar. Oil, fats, grease, all of those are non-polar. And because they don't have a positive or a negative side, the water doesn't mix with it. Water is only looking for other positives and negatives non-stop. And because oil doesn't have any positives or negatives, it gets pushed out to the side so that the water can bond with other positives and negatives. We end up seeing this in the magic that is soap. So oil, grease on your body is non-polar. Water doesn't like it. So if you go and stand underneath a shower, the water is not really going to take away the oil. What you need to do is, first of all, scrub, and second, use some soap. What ends up happening here is that soap has a polar head and a non-polar tail. So when you get shampoo and you start scrubbing your hair, the non-polar tails will bond to the oil in your hair, and then the polar sides will bond to the water. So that way when you stick your head underneath the shower head, you will wash away that dirt and oil and grime and grease. So, soap, please use it. Please shower regularly for me and for the person sitting next to you. So, what we're gonna do later today, this is just 3 ingredients. We have milk, we have food coloring, which is the dark area in the middle, and we also have dish soap. We're gonna be looking at why that happens later on. I'm gonna let you guys make your own, and hopefully you'll be able to see how and understand why and kind of like revel in how cool it is. So now let's start talking about pH. Water, while it's got the 2 hydrogens and 1 oxygen, this oxygen over here is getting pretty close to that hydrogen. This oxygen and that hydrogen are super close to each other. And sometimes this hydrogen will actually hop onto the other oxygen. Opposites attract, right? Which leaves a compound called hydronium, which has 3 hydrogen atoms and 1 oxygen, and hydroxide, which only has 1 oxygen and 1 hydrogen. Because there's an extra hydrogen, we end up having an extra charge. Hydrogens, after all, do have a proton, which is that positive charge, and oxygen's very electronegative, meaning that it loves to hold on to electrons. So we have a beautiful scale here, and this is your pH scale. It goes from 0 to 14. At 0, we have 1 mole of hydrochloric acid, and eventually you guys will know what molarity is, but we're not going to worry too much about it today. So hydrochloric acid is as much acid as you could possibly get. It is a ton of hydrogen ions. And notice, close to it, we have gastric juices. That's in your stomach. That's stomach acid. Your stomach acid is really close to one of the strongest acids on earth. We have orange juice, we have wine, we have coffee, we have milk. All of these things are acids. And then right here, smack dab in the middle, we have water, pure water. Blood is a little bit basic, and then we have seawater, detergents like Tide Pods, please don't eat it, ammonia, bleach, and then sodium hydroxide. And all of these bases are very corrosive, just like how these really strong acids are corrosive as well. So we go from 0 to 14, and our middle is 7. I know that seems kind of strange because we like to think going from like 0 to 10 and 5 being the middle, but here we're going from 0 to 14 and 7 is the middle. If it's under 7, that means that it is acidic. If it's over 7, it is basic. So, what happens when water reacts with acids and bases? You're going to see ions. Now, an ion is any charged molecule here. So you add an acid to water, the water is going to dissociate, so the hydrogen ions are going to pop off of each other, and they are going to float around in a higher concentration. If you add a base, we're going to see more hydroxide ions. So, more hydrogen ions, more hydroxide ions. With acids, any compound that has a ton of hydrogen ions. Now, eventually, if you're really into science, you'll learn about another way that acids can be formed with electrons and whatnot, but I'm not concerned about that right now. What I need you to know is that acids have hydrogen ions, values below 7, and examples: vinegar, tomatoes, stomach acid, coffee, and of course, hydrochloric acid, hydrogen chloride. We also have bases, which is where we get the hydroxide ions from. We call this alkaline. So acids are called acidic, Bases will get the alkaline term instead. This is above 7, and it includes soaps, bleaches, your blood is slightly basic, baking soda, Tums, all of these different things are bases. And that's where you're going to see that high concentration of hydroxides. Now, bases are extremely, extremely corrosive, which is one of the reasons why munching on Tide Pods can do some serious damage. They are a very, very strong base, and that will eat away at the flesh inside of your body. So our pH scale, and this is going to be a little redundant, we've seen this before, goes from 0 to 14. It measures how many hydroxide ions are on there, and it's a logarithmic scale, not that we're going to be going over that, but a low pH means more acidic and more hydrogen ions, and a high pH means more basic and more hydroxide ions, and then neutral is at 7, where we have an equal amount of hydroxide and hydrogen. And oh my gosh, guess what you get when you take 1 hydrogen and 1 hydroxide? H2O. That makes water. So strong acid plus strong base means water. Buffers. This is when we take a weak acid or a weak base, so it can react with a strong acid or a strong base in order to neutralize the pH. The pH of the human body must remain in between 6.5 to 7.5. And even then, your blood is at 7.4. Your blood is based off of how much acid is in there. And we have these bicarbonate ions that are there to help neutralize the pH. That way it doesn't get too extreme. Because if your pH goes out of whack, it's going to break down a lot of the tissues in your body and you can die. So I would like for you guys to know this pretty well. Please fill this out. Please draw this out. The scale is measuring the amount of hydrogen ions. It's really hydroxide ions, but hydrogen ions. And it ranges from 0 to 14. Below 7 is acids. Above 7 is bases. 7 is neutral. You gotta have this down. There's no excuse for not knowing it now. And finally, here's your summary. Water is polar or nonpolar. Draw and label a pH scale. Which side has more hydrogen ions? Which side has more hydroxide ions? Why do we need buffers? If you have any questions, please just let me know. Outside of that, make sure that you have your note taker finished. If you are finished with everything and I have not called you over in order to do the lab yet, go ahead and start your vocabulary chart. Good luck, guys. Bye.